You are coming into the latest presentation of this event here in Green Park Hotel, and I also want to say thank you to the association to invite me here to keep this presentation. First of all, I want to introduce myself. My name is Martin Kunz. I'm working for organic peroxides since 34 years. This is quite a long time. I finished my education in the 80s as plastic and rubber technologist. Today I'm responsible for the applied technology department, doing technical support. And so I'm sure that I can give you a lot of information about peroxides. An error occur, okay. Let me check. Okay, first of all, I want to introduce my company as a global player, maybe even the #1 in supplying peroxides worldwide to the thermoset market as well to polyolefins and rubber and plastics. Then I want to show the major applications for thermosets based on peroxide curing. I would say in the last 10-15 years, there was not a new development of a new fantastic peroxide. The industry knows very well the products, but I think it's a good idea to make assumption of all possible applications. And then I want to talk a little bit about the safe handling of this kind of chemicals, which are different from others like solvents. And there are some risks to handle and store this kind of peroxides. Now, the history started in 1911. We have been founded near to Munich in a small town. We are producing hydrogen peroxide as a bleaching chemical. This was the startup. On the same side was Linde, which are doing chemical gases, producing chemical gases. In this small area starts a lot of industry at this time, and I don't want to pass over the 2 world wars because the plants were completely destroyed this time. Okay, thank you. Continue with 1961, we had a joint venture with Laporte Chemicals. This is a very big English company supplying different chemicals to the industry. Then we are ending in a joint venture with Solvay. And Solvay, as a partner, is using the hydrogen peroxide, and we use the hydrogen peroxide to make organic peroxides. And this time starts the industry to develop all these applications like polyolefin polymerization and curing of polyesters, vinyl esters, methacrylates. This was the time where most of the peroxides have been developed. Ending in 2001, Degussa, a very well-known brand, decided to increase their portfolio. They bought a lot of chemical companies like Goldschmidt, Röhm, SKW Trostberg, and so also we end in this big agglomerate. And in 2007, they changed their name to Evonik, which is more artificial name. It's a new brand. And they decide to sell again everything what is not core business. They sell again to the industry. Oh, okay. Okay. Okay, now it's maybe better, but so small that even the normal voice is enough. Okay, we are ending now as United Initiators under umbrella of an investment company called Vision Capital. The United Initiators part is standing for a group of organic peroxides producers located in the US, located in Australia, and in Germany and in Sweden. You see here our newest acquisition is the Surges Group. Maybe you already know the trade names Norpol, Norox, Andonox, and this portfolio is now integrated in our basic Curox plant. And they had two sites, one in Köpmansholm, Sweden, and another one in Helena doing MEKP, AAP production, as well as in US also per-esters. And our old plants are Illyria doing per-esters, raw material, hydrogen peroxide, Mobile USA. Then we have in Australia for local consumers, local MEKP production. And in Shanghai we have now a trading platform. But the center and the core of all this is located in Pullach. There is the Applied Technology Laboratory. And from this place I visit you here. I just want to assume all these kind of applications you find on the thermoset market, the cold curing, elevated and high temperature curing, very well known filament winding, gel coats, hand layup, spray layup, RTM, BPO for different applications like methyl methacrylate curing or chemical angers, the elevated temperature curing, for panel manufacturing, then some injection for methyl methacrylate, artificial stone, then the cured in place pipes using polyester to recover damaged pipes, then the high temperature curing, basically artificial marble, which is not a real, it's a composite stone, it's not a glass fiber product, the pultrusion, and finally SMC, BMC. First of all, before I showing any curves, I want just to explain our perspective how to measure such things. We are always using this kind of double-walled glass tubes because the measurements in this kind of glass tubes is very precisely. The airspace here avoids that the heat is transferred to the bath and taken away, so you can make very good comparisons, one peroxide dosage to the other. If you have only a paper cup, you may have a strong influence of the environment, bath, and take the heat away. So this is also regulated by the DIN norm, and I think it's common practice in the development of resins as well, like DSM is doing such things. Then the curing performance, okay, cure time, gel time, peak exotherm, mold release time, hardness sparkle, residual styrene. Most of the customers don't do that, but it's a good indicator and it's not so difficult to use a gas chromatograph to analyze the rest of styrene, which is not polymerized, which indicates the curing performance and also the environmental issue. Then aging under climate conditions, TOC, by the way, TOC is important for the automotive industry. Total organic carbon is also done via headspace analysis. Then the osmosis test we do mainly for J-code for marine application, and I have an example later on. So now this is the big portfolio. On the left side you see phthalate free, on the right side you see dimethyl phthalate products. Why existing these two lines of MEKP products? It's simply a matter of regulation under REACH. It was clear that phthalates will disappear. They are not allowed to be on the market again. There is existing a list, it's called SVHC from Helsinki, substances of very high concern. And so we decided to set up only phthalate-free MEKPs. After the evaluation and the dossiers for the REACH, European regulation, new regulation of chemicals, it was found out that you can still use DMP. So the Swedish plant brought all DMP peroxides with them. So we have now two lines, one phthalate-free, one based on dimethyl phthalate. Starting with the nomenclature, you see here M102 is the slowliest one. It's also suitable for vinyl ester. It doesn't form, so it has very good properties if you need a long pot life. 302 is more or less a standard grade. Medium water hydrogen peroxide content. It's a universal general purpose type. 312 is a little bit improved. It's definitely suitable for gel coat appliance. It's tested from Büfa Kompozit, which is our partner in many boat builder areas. So this is definitely approved for gel coats and gives a good quality. The 402 is a very strong and fast one. It's mainly also here in Turkey, we sell it to the bottom industry. The fastest one, and for the dimethyl phthalate range, you basically find the counter types. M103, M104 are very slowly one. The 103 is more for vinyl ester. 104 is a general purpose one. Then 303, this is the working horse. Working horse means there are certain brands, I don't want to tell the name, but they're all offering one big standard which goes in big volumes to the industry. And the 303 is one of these counter types. We have here also the 105. It's a little bit modified 303 for summertime. It gives you more space to work because the pot life is a little bit longer. When you have 29 degrees, you may adjust your performance better with the M105 because the ambient has a very high influence on the curing. 403, 404 are dedicated for special customers. Behind each peroxide is a group of customers, of course. They are medium reactive, and the 503 is definitely the fastest one, similar to the 402, but based on dimethyl phthalate. Then we can offer today certain blends, the Curox CM types. These are blends between cumene hydroperoxide and methyl ethyl ketone peroxide. The target of this product is to reduce the peak in processes like infusion, where you have different diameters, thickness of the parts. You can cure very good without having any stress in the material because the peak is not jumping up. It's more moving flat, but ending in a final good quality. There are certain blends depending from your requirements, and MEKP AAP blends are also very well known. As example for RTM, we offer such a blend. We come later on to that. And then we have the MEC. This is a gel coat premium type. It's more expensive than the others because it's based on a special synthesis. It's not a simple MEKP, it's something modified. But with this one, you get a faster cure, harder surface, lower tackiness, and absolutely reduced porosity. But today, it's more a smaller product, but we hope that it will grow in future. Now, you see all these MEKPs, but you have no idea what is the difference really. I show here now this comparison chart. Some of them are here inside, and then you can see that M503 supplies you a very fast chill time, ending with 103 with a very long chill time. You see the blue bars. You can adjust according to your requirements exactly which one fits into your process. The same to the peak exothermal. You see here different exothermal peaks. If there is a problem with stress in the material because the temperature peak is too high, you can say, okay, I want to try, instead of 404, I want to try the 302 or something. Yeah. Good. Now, why are all these MEKPs so different? Because it's just a synthesis. The background is very tricky. The MEKP synthesis is not a simple putting two things together and then comes one product out. It's definitely the case that you have here three different kind of MEKPs. Yeah? And this creates the different performances. Also, the phlegmatizer has a certain influence on final properties like the speed. Some phlegmatizer can reduce the speed because they react with cobalt octate, which is also used here. So they interact with cobalt, and it may possibly give a lower reaction. So the influence is also on osmosis. If you chose, it's not mentioned here, but if you chose diethylene glycol, you can have osmosis because the water likes diethylene glycol and easy can make this osmosis exchange and comes to the fiber is swelling, and you get the blister. So this is very important to choose the right peroxide with the right phlegmatizers. Then we have the hydrogen peroxide content. This we need to accelerate the MEK piece. So you find always a small amount of that inside. But on the other hand, if the amount is too big, you get blistering because this is forming oxygen. And H2O2 is simply to explain when it decomposes, there will water and oxygen come out. And this can affect the quality of your surface, the quality of osmosis resistance. And it also affects the curing speed in vinyl ester. Now, also we have the cobalt accelerator and the amine cobalt blend accelerator. They also can trigger a little bit by making a complex with the phlegmatizer, the speed. And of course, there is a wide range of resins. The resins can double bonds, are they stabilized, pre-accelerated? So although that one has influences on the total performance. Then I want to come to the ambient problem because we did some measurements. You see the MEKP compared to the AAP. You see that the influence of temperature is very strong. At 15 degrees, the reaction is nearly flat. The exothermal is not enough. But if you have maybe 20 degrees and above, the performance is maybe sufficient, but you see that the speed is dramatically different. This is why you need to adjust by dosage. There is a limited possibility, or by cobalt dosage, or choosing a summer version of the peroxide. Then you see AAP is much more stronger. It doesn't lose so much enthalpy. It remains the peak, but the chill time is getting very long. Yeah. Here's such an adjustment. You see 25 degrees M303, 25 degrees 105, and if the temperature increases, you come more closer to the 303. This is a possibility to handle such things. Now, you read before, in the slides before, you read always fading red. Fading red means the product has a red color, but this is not a simple pigment. When the reaction goes on, the red color starts to disappear slowly. So this is an indicator. Here's a filament whiting example. You see here, you can see on the one hand the layers, how good is the thickness of the layers, and the homogeneity. On the other hand, you see when the curing reaction is done. So this is a good trick to watch your reaction. Then we have the point safe handling. Everywhere where we have this red liquid, you see, there is a peroxide. We have one accident in Spain. They switched to red-colored versions because it was a change by mistake. They didn't recognize that this is peroxide, and then they had a problem. So this is another point, the safe handling of this product. You can easily see where it is in the vessel, in the dosing line. Now, just a short view on the J-code hand spray layup application. Very much standard is the M303-312. One is phthalate-free, one is with dimethyl phthalate. The MCH as a premium hardener, 102, 103 for the vinyl ester J-codes. And how we do such an osmosis test, maybe you also sometimes do something like that. I just want to show how we do it. We pull a film with 700 microns, then the styrene comes out slowly, then the film is shrinking, it's not shrinking, but he's losing thickness, coming down to 500 micron, then we make the lamination. You have to wait minimum 45 minutes, and then we cut out the pieces, put it to a tank at 60 degrees, 28 days, and additionally 20 days, 75 degrees, circulating demilitarized water. And just some examples. So there's one slide missing. Okay, there is one slide hidden, unfortunately. Then I explain it like that. If you get water to the fiber, it starts to swell, and the blistering begins. This can happen if you have porosity or a thin layer of gel coat, too thin, or a wrong gel coat. That means not suitable, it's not elastic enough, you get cracks and the water can go to the fiber. So here we have A390, I expect, let me check, I think the switch, the error message killed some of my sheets. Yeah. Check that one. Yeah. Okay. Okay, I continue. The AAP, there are existing also different modifications. The A300 is the standard, but for the filament winding, you need possibly a little bit stronger reaction. So here you see the A390. There's a slightly increased peak. There is a periester inside. This is reacting after the AAP comes the periester and get another higher peak. More of that you can have with the A335. You have another step here. And yes, this is how to improve the performance of the AAP. If you use temperature like 40 degrees, some of the filament winding companies, they have infrared equipment to heat up a section, then it's a little bit different. The standard AAP is slower than the A390. So the A390 is sold in big amounts to this industry to improve physical strength, and finally also the residual styrene. This example shows if you have really thick parts, like that one, this kind of fitting, or this is a socket from an antenna, the raw material, the raw produced parts, and you have 10, maybe 5 centimeters or something, or 10 centimeters. You can easily adjust the exothermal using A140. Gives you a really smooth reaction. The peak is not very big, and the curing is already very good and finished. You see that below this peak is a lot of energy. So it's curing smoothly over the time. Here you have a few, again, on the different A300 standard. By the way, A300 we don't recommend for J-coats because due to the production, it always contains a lot of water. I think there is no quality which is on the market which has lower than 6-7% water. And it also reacts with cobalt a little bit different. The color reaction with cobalt is stronger, so you may have not a white gel coat, sondern it can appear a little bit greenish. So the AAP is definitely in the marine area not recommended. We heard before RTM, possibly if it's colored, and so it may be possible. A140 we already explained, 335 also, 390 also. Okay. Now coming to the RTM, what we found on the market is a blend. Of course, A300, yes, AAP here, very strong peak. The M312 is a little bit earlier reacting, giving a lower peak. And so we advise to use a blend of both, and certain customers using this blend, because then you don't get the steep reaction, a smooth reaction starting earlier, and you have nearly the same mold release time than with AAP, but not the stress in the material. Then cumene hydroperoxide blends I already mentioned. You see that CP50 to CM85, this is the ratio of the components. The CP50 is definitely only for vinyl ester because it's basically cumene hydroperoxide. The other one are affecting the exothermal peak and bring it down. Very common is CM75. It can be used also in fusion, and it's more or less the working horse in this field. The other one are specialties. Here you see the effect of peak reduction. You see here a standard M104 slowly reacting. Then you see the CM85 lower peak but the same speed, CM70, and you see here the working horse CM75, lower peak, longer pot life than a standard slowly MEKP. And this one, maybe it's not sufficiently cured. This must be checked more in details. But coming to the curing performance as such, if you compare in a DCPD resin, 2% standard MEKP with 2% CMD75, the first 4 hours the residual styrene is quite high. But after 24 hours it reached the same limit because the cumene hydroperoxide is polymerizing more and more. Yeah. 12 millimeter laminate, which is normally not suitable for 303. I think there is some problem with this laminate, quite hot. You see here that you have from the beginning on better values with the CM75, and the dosage is of course much lower. If you have a resin, then you have to decide, it's forming or not. So what can I do? Then you should just look in the portfolio what you can get from the supplier, and you will find out that the forming is different. And the upper row may be acceptable, the lower row is definitely not so acceptable. The oxygen inhibits the reaction, makes the surface tacky, and you see here 102 is the most reliable. CM50 contains less MEKP, also reliable, and this both may sufficiently curing, and you can handle this kind of oxygen formation. Now we came to the next kind of products. We have here the BPO, just to mention. The BPO is very well known for car putty and doing things by hand. Some of them even use it in pultrusion, I heard, but I don't know the end result. But definitely BPO is a standard for simple work. The residual styrene is always a little bit higher. It reached maybe 3-4% residual styrene, which is not a high-class performance. And so we find it in road marking, in floor coating, mainly based on acrylic resins, and but also in chemical anchors and mine bolts. And it's accelerated only with amines, not with cobalt. These are the different supply versions, liquid suspension, sprayable, and powder forms. And the benefit of this product is if you have 5, 6, 7 degrees cold flooring or cold mold, it will start and react. This is a difference to the MEKP AAP. It can be used at lower conditions. Now the panel manufacturing, also meanwhile very much standard here. The I300 methyl isobutyl ketone peroxide is the all over standard in this industry for continuous laminating, starting with 40 degrees to 100 degrees on a continuous line, maybe 60 meters long, whatever. Also in Turkey, I know some of them who are doing that. mainly one big one. And these are also pictures from our customers. I'm allowed to show that. Yes, the requirements are you need a long pot life because you have a resin bath, and from this resin bath you dose, and you cannot always change fast the resin bath. So you need 2 hours, 3 hours pot life, and the MIKP is much slower than a M102. There is another process, table process. They use the same blend I showed with RTM, M370, MEKP, AAP, and for corrugated sheets, I think you don't need the MIKP. These are smaller plants, not so long curing, so you can use a standard MEKP as well. Also important is the climate resistance, of course, and the discoloration in the sun test and all these things. And the residual styrene should not be below 1% in this case, because this kind of customers want to coil the product, and if it's 100% cured, it's very stiff and you cannot coil it sufficiently. Now here you see the reaction at 40 degrees without cobalt, then 40 degrees with cobalt, a big jump, 60 degrees with cobalt, and 80 degrees without cobalt. So you see there is a lot of adjustment possible, and you can adjust it to your process. Now coming to the next peroxide group for the elevated temperature curing. This blend is mainly used for elevated. You get 2 peaks. PCHPC is a peroxide dicarbonate. It has nothing to do with the ketone peroxides. It's a powder, and it must be transported, temperature controlled, and stored, transported, controlled. This is the first peak, and then comes the per-ester, the TBPB. This is a heating rate in the DSC, so we spread the peaks in this measurement. In practice, it's more a flat curve. But all these applications need a second oven step or curing oven step, whatever, to decompose the peroxide completely. This is one of these applications. I don't know how far it is in Turkey. In Europe, this company is called In Situ Form Norditube. However, they are doing this. In industrial areas, they repair the damaged wastewater tubes, and they pull in such a fiber socket which is impregnated with resin and peroxide, and you have this problem of the BCHPC. You must transport it at 5 degrees around to avoid any pre-curing on the truck, because this could be 30 tons or something, big inliners. And so you can add some inhibitor to protect it from the pre-curing. And on the place, you bring it into the ground, and then you purge hot water inside, and this will start your curing with the BCHPC, and after 4 to 6 hours, it's cured by the TBPP. So you have this kind of 2-step reaction. Pultroschen is exactly the same recipe. They also use the combination, this industrial standard peroxide dicarbonate plus per-ester. It's different process, but the recipe, peroxide recipe, is nearly the same. They need in the dye a high reactivity, and later on post-curing step. Alternatively, there are some others you can use as replacement, or if you need a second step, or you want to have not sensitivity against fillers and pigments, then you can use a perketyl. And so there are certain possibilities around the standard. Just to mention shortly, injection of methyl methacrylate using similar recipes. You have a vessel with filler and methacrylate color pigments. You inject it in the mold, and then you get a nice part. The BCHPC is definitely suitable for methyl methacrylate resins. Coming to Breton technology, They are using only this per-ester. It's only 7% of resin inside. They need a strong reaction, but a long pot life because they have to mix all these minerals and glass flakes in a big container, bring it to the mold, and then the TBBP starts to react in the mold at maybe 100 degrees, 30 minutes. So these are the standards. You can add some cobalt to accelerate. TBBP is acceleratable by cobalt. Now coming to the SMC, BMC, this is one of our core industries for the per-esters. We are market leader in this field for peroxides. You know all these products. The first one is automotive parts. The second one is electrical insulation, cabins, whatever. Or then BMC products like this headlights or this kind of cabins for neon lamps. So here you see the applications and which peroxide we chose. We don't choose ketone peroxides. We don't choose peroxide dicarbonates. We chose between perketals and per-esters. The perketals definitely are not so sensitive against fillers, against pigments, carbon black, and so they give a certain safety for the pre-preg in the transport or warehousing. The efficiency is not degrading over the time. The perketals are not so sensitive. TBBP is the widely used standard, but it has the problem with the carbon black. And the TBPEH here is added as an accelerating component. It decomposes faster and can be mixed with TBBP or mixed with perketal and getting a fast kickoff. It depends from your flow time, mold release time, what you want to have. By the way, we have here TMCH HM1. This is already mixed with per-ester and perketal. And I'll show you later on a picture what is possible with this product. And the TBPHC is now, in the moment, the standard in the automotive industry for low emission for the internal parts. It's a monoperoxycarbonate, different from the others, mainly used for low emission products. This is now the TMCH HM1. You see a very complicated part here, BMC part. You see the exothermal peak, TMCH, and you see the HM1, which gives, because it's a mix of two peroxides, give a more flat performance. And this product is a longer time ago when Freudenberg makes this product, but you see it's quite complicated for a polyester product. This is the overview over the whole range. Fastest one, TBPEH, the kicker. Latest one, TBPP, between the perketals. So also here, possibilities to adjust your performance. Then coming finally to the emission. The SMC customers require always low emission because internal parts of cars, the fogging of headlights can result in blind glasses. This is longer time ago. The old cars, they have sometimes a little bit foggy. This comes from the SMC. So they are still working out recipes with low emission. You see here the volatiles, acetone, epoxystyrene, the headspace analyzer. There is an oven, you heat it, and the gases are analyzed by gas chromatograph, and you get out all these emittents here. The norm is VDA 277. Now, with the peroxide part, I'm through, roughly cover all this kind of applications. Now coming to safe handling of organic peroxides. Just for people have a warehouse or a stock in their plant, you see that mainly important is this area, so-called SADT. This is the self-accelerating decomposition temperature. When you have, in summertime, outside 60 degrees and you are using TBPEH, the per-ester, even the empty can which you put outside of the plant can give you a problem because the rest of the peroxide, the 200 milliliters, can burst the can and can even create a fire. So always keep your eyes open that the warehouse and the stock and the waste doesn't exceed the SADT, the self-accelerating decomposition temperature, which is for TBP age 40 degrees. The MEKPs have slightly above 50 degrees. And before is the storage, transport temperature, and your emergency alarm for the warehouse. What happens if something happens with peroxide? Every manufacturer, others, we had sometimes had an accident in the past. The peroxide decompose, all peroxides are decomposing in other high flammable components. And this leads definitely even to ethane and isobutan. So you can imagine that you easily can create a second fireball. This you see on these pictures. This is one pallet of a periester decomposing. The warehouse should look like that. Sprinkler, pressure release side. If something happens to release the pressure, you have a concrete floor. You have outside alarm system. And in Germany, we have the BGV-B4, which gives the advices, the regulation, how many can you store on your working place, how many can you store in a separate room in the plant, and if you need extra building or not. And last but not least, never store peroxides with other chemicals. Cobalt octate or something like that is very dangerous. And this is the last advice I have. And then I'm through. This is our plant here in Pullach. This is the River Isar, and 15 kilometers away is Munich. So we still produce in an area where normally people drive bicycle. So I thank you for your attention, and if you have any questions, let me know.